Okay, and I have to deal with some muting issues in just a second, so stand by. Okay. Good morning, Cycle 25. Welcome to yet another session. Today we're lucky enough to have John Portune with us to take us through a presentation on In Search of a Perfect Mag Loop. John, take it away.
So, good morning, everyone. And let me get this up to full screen. Come on. Where did it go? Where did it go? Oh, well, let's try again down here. Come on, open up. All righty. We've talked about this to some degree in the past already, so I ask you to bear with me for the fact that you've seen some of this, but I finally put the PowerPoint together and to use in part of my general lecturing around. So I'm bringing it to you today, and I'm pleased that you're allowing me to do it, so you can give me feedback on it, since it is a production and still somewhat in the development. But I call it, as you can see, the search of the optimum mag loop, which is not something most hams think about. We all know that the mag loop is, of course, a very popular design, great for home builders and so forth. And here's just a bunch of them that I took off the internet, including some commercial ones. But most of these loops are not optimized. People build them mostly by guess and by golly, or they just follow somebody else's cookbook and they don't know why that's right. But since that's what they saw, that's what they built. But many of them have very high loss, and many of them have much higher cost than they need to have. And a lot of them are hard to build. They're difficult constructions. And some of them are awkward to use because they're heavy and big and so forth. And of course, lots of them are neighbor unfriendly. The neighbor looks over the fence and says, "What's that ugly thing in my backyard?" Today, I don't want to look at the benefits of a mag loop. I think most people know what mag loops are. Most hams do, but and even newbies are aware of them. But I want to talk about the 6 factors that any designer or buyer or purchaser of a mag loop need to keep in mind to ask yourself, what makes a mag loop optimized? Not what just makes it attractive in price or neighbors or what, but all the factors. What are the 6 factors? And then I want to show you my version, which has finally been finished and has been on the air by several other people, rather impressively, as a matter of fact, and show you my design. It's a very inexpensive PVC and foil tape example. For starters, there isn't one optimized design. The optimized mag loop optimization depends on your situation and your need. So something optimized for Joe Smith and George Brown are different, but they both need to be optimized, not just partly optimized. I also here am looking for what I call the epicenter. That is there one sort of design that fits the biggest majority of hams? And this is what I call the epicenter, or the quasi-universal design. And that's what I'm in search of, more or less, in this presentation. To optimize a mag loop, we need to optimize these 6 factors: shape, size, conductor diameter, conductor material, and the matching and tuning mechanisms that are used with them. Because all of these can cause a loop to be very unoptimized, particularly if you leave some of them out, as a lot of home builders do, and even a lot of the commercial builders do. Because you must also weigh all those 6 factors against performance and cost and construction needs and awkwardness and, of course, stealthiness for your neighbors and HOAs. All right, let's look at the factors. loop shape. Here's the original mag loop that had appeared in ham radio back in 1968. Lou McCoy, who now Silent Key, but was a luminary in ham radio, wrote this article in 1968 based on the Army loop, as it was called, which was a design by Kenneth Patterson, as you can see here, for use in Vietnam. The Patterson's Army loop was 12 feet in diameter, made of 8 5-foot bolted together sections, as you can see here, for conductivity, and used 3 big, difficult, expensive, hard to use variable capacitors for tuning and matching. His loop was not optimized, but it was the beginning of the mag loop. By the way, you can find this article on the QST old article archive. That's where I got this one. The mag loop, or the Army loop, is still in use, but it's taken more this form as we see today here. What's interesting about the shape of the loop, and this is what we're bringing up here as the first factor, shape, is that shape stuck in the mind of most hams, a circle or an octagon. To most hams who get up to build mag loops, they think that's the shape it should be. That's the optimum. But no, that shape is not optimum, as I'm going to show you. Michael Faraday, back in the middle of the 19th century, learned that small magnetic loops, which he played a lot with to come to his 2 laws of magnetism, realized that a loop, a small loop of wire conducting current, AC or DC, whatever, does not work because of its shape. It works because of its area. And therefore, the only thing that really matters in the shape of a loop is the area inside of the loop. But think of this, a 3-foot circle, that one on the left, that has the area of a 3-foot circle, is only 4.5 inches smaller than a square of the same area, the one you see on the right over there. That's trivial. That doesn't make it, it's not that important to make it round. And you certainly don't need to make it octagonal. That doesn't do anything for you. Gets a little closer to a circle, but we don't need to get close to a circle. As Faraday proved, it works by area. Because round is hard to build, particularly if you do it in large tubing, which is very important. Round is not the optimal shape. And an octagon, of course, is sort of a form of a circle, and it's not an optimum shape either. It has expensive elbows if you try to build it out of copper and so forth. To me, the square, which is the easiest form to build, is the optimum shape for the magnetic loop, not circular, not octagonal, not something else. All right, that's the shape of the loop. How about the size? Well, there's several factors at work here which most loop builders don't take into account. And this particular company in Italy who produced this antenna that you see here, the Ciro Mazzioni automatic magnetic loop antenna, didn't take it into account in their building. But because for magnetic loops, yes, it's true that big is better for lower frequency, but big loops have some big disadvantages. They're awkward, heavy, large, difficult to turn, difficult to rotate, difficult to mount, and neighbors hate them. Also, something that most mag loop builders don't consider is that mag loops have a maximum frequency, and it has to do with size. Consider this. Here's a simple square loop, what I consider to be the optimum shape. What's its maximum usable frequency? Did you even realize it has a maximum usable frequency? Oh, yes, it does. What is it based on? It's based on self-resonance. Any coil, and of course a mag loop is just a big one-turn coil, has a natural inductance of the conductors. All wires have inductance. And all wires, particularly in a loop, have capacitance, mutual capacitance between parts of the loop. Those two reactances form together to make all loops, all coils, self-resonant. And self-resonance is the determining factor in how high a frequency a magnetic loop can work. For example, a 4-foot loop, which has a natural self-resonant just about 30 megahertz, 32 megahertz, will work 10 meters. But an 8-foot loop will only work at maximum 16 megahertz. So it will work 20 meters maximum. And a 16-foot loop, like that big one you saw in the previous picture, will only work up to 8 megahertz or 40 meters maximum. So a lot of home builders who are trying to optimize their loop for their situation don't even realize that this limit exists. Also, here's another factor which I throw in because it's seen in the literature, and the literature is very good at obscuring the important details. A lot of articles on mag loops say, don't make your mag loop bigger than a 10th wavelength. That's not true. It's just not true. And I'm going to show you why. In fact, it's so common that if you get out the mag loop calculator, which is the one I use all the time, and there's several of them out there, it'll come up with a big warning box, just like this one. Don't make your loop bigger than that size. It's too big. Make it smaller. No, you don't need to do that. Ignore this. Why does this exist, though? Why does so many websites say, don't make your loop bigger than 10th of a wavelength? It has to do with the somewhat false assumption that mag loops get rid of local noise. Well, to some degree they do, but much less than most hams think. Let's understand this 10th wavelength thing just quickly. There's a mag loop there in the middle. And like any antenna, it has 3 fields that are defined around it. The near field, which is made up of 2 smaller sections, and the far field. This is where the wave is out there in space that comes out from this antenna. And when the wave from any antenna gets out into far space, or the far field, which is most of space, it takes on a very fixed relationship between its magnetic and electric field. They're at right angles and in phase like this. And as such, they travel, they radiate. That's why they're called it's called the radiating far field. But very near the antenna, within a very short distance, and it's actually roughly 2 wavelengths at most, there are 2 smaller fields called the near field. And you may have heard of the near field, but though most hams don't know much about it, I'm only beginning to really come to understand it better. Even it has 2 parts. The inner near field is called the reactive field. It's only 1 wavelength in diameter. And the radiative outer field, which is called the radiative near field. The interesting fact is that as a radio wave makes its way away from an antenna, it transitions between the field there in the near field and the field in the far field, and only becomes that far field pattern after it gets 2 wavelengths away from the antenna, roughly speaking. And of course, it's dependent on wavelength. Hence, on 80 meters, the size of that inner circle is 125 feet. Keep that in mind. Faraday, back in the middle 1800s again, a real pioneer, a real genius, realized that inside that reactive inner near field, that a magnetic loop, or a small loop, only reacts to the magnetic field. In fact, there's hardly any electric field inside the loop at all. It's mostly all magnetic field. And that's what does the reception when the radio wave comes up. That's why a mag loop is called a mag loop, because it picks off the magnetic component of the wave coming in. But inside any small loop, the magnetic field dominates. Therefore, a small loop is insensitive inside of itself to local electric fields and some local QRM. And this is the thing that makes So many websites say, don't make your loop bigger than a tenth of a wavelength. Oh, you can make it any size you want to, frankly. You can ignore this, but that's why the sites say that. It's because it has to do with the supposed reduction of local QRM. But to make use of this property, and it's a real property, your interfering signal, your power lines arcing away, has to be within the reactive near field. And for 80 meters, that's only 125 feet. For 40 meters, it's only 60 feet. For 20 meters, it's only 30 feet. So if your source of noise is not within that reactive inner field, the magnetic loop doesn't get rid of it. Therefore, all loops work fine. Don't think that making a big loop is a big error. It's not. Because as a magnetic loop becomes bigger, it only becomes a conventional loop, and all sizes work. And as it gets bigger, it only loses a little bit of that noise immunity, which is largely a myth. All right. Factor 3, conductor diameter. This is the biggie. This is the one that all mag loops must pay attention to unless they want a very unoptimized loop. And that's why most of the loops you see on the internet, most of the designs that other builders use to build their loops are only built by guess and by golly, and they don't take this into account properly. In fact, even some of the commercial manufacturers don't take it into account correctly. Let me demonstrate this to you. Here's my 4-foot square loop. This is a diagram or a chart based on my 4-foot square loop. Suppose you make it out of 3 different size conductors. 2-inch pipe, which you'll see is a kind of a magic size. Or you do what a lot of loop builders, they build it out of RG8 coax, which they think, oh, that'll make a great magnetic loop. No, it does not make a great magnetic loop. Or some of them are dumb enough to use number 10 wire and stick it inside of a PVC frame. That's a terrible way to make a magnetic loop, because look at the loss figures that you get here if you do that against frequency. Look at the efficiency of a 4-foot square loop made with these 3 materials of these diameters. A 2-inch pipe, piece of RG8 coax, and a piece of number 10 bus wire. What's the efficiency of those loops over the HF band? Well, you can see it there. It's all plotted for you. Is that only a piece of 2-inch pipe or bigger has any usable efficiency at 40 meters. The others, piece of RG8 or 10 wire, they aren't usable at 40 meters. RG8 is barely usable down to 20 meters. And a piece of 10 gauge wire is hardly usable at all. So realize the biggie in magnetic loop designs is to make the conductor big in proportion to its diameter. And here's approximately where the efficiency falls apart at about 50% loss. That's a fair amount of loss, but it's a workable amount of loss for most hams, 1 S point. This is why I consider for a 4-inch loop, you've got to make the pipe at least 2 inches in diameter. That's the optimum. If you don't want an optimized loop, well, then make it out of RG8, but that's not an optimum loop. Here, for example, is a good example, well-known example of a magnetic loop that is not optimized. That antenna, that MFJ loop, as popular as it is, and as reasonably well built as it is, has low efficiency below 20 meters. So if you think that MFJ loop's going to work well on 40 meters, forget it. What they're selling here is that box on the left anyway. They're not selling the loop. That loop is too small in diameter. I mean, the conductor's too small. Why do we need large conductors? Well, here it is quickly. All antennas have these 4 properties: inductive and capacitive reactance. We know this. This is what makes a loop, any antenna, resonant. But they have 2 resistances: conductor resistance and radiation resistance. Radiation resistance is what space does to an antenna to allow it to take radio waves. Conductor resistance, though, makes heat. It wastes the power that you put into them from your transmitter. Radiation is resistance, the property of space loading any antenna, is what makes the radio waves. That's where we want our transmitter power to go. It's the good guy. But as the size of an antenna goes down, the conductor resistance, the bad guy, only goes down slowly directly with the size. But as the size of a loop goes down, its radiation resistance, the good guy, goes down as the square of the size reduction. So a half-sized loop has a quarter the efficiency of its bigger cousin. And why do we need all of this? It has to do with skin effect. Skin effect, as we know, is the fact that the current only flows on the outside of a conductor. And this greatly increases the conductor resistance and greatly lowers the efficiency. That's why mag loops need big conductors. So small conductors are the biggest cause of low loop performance. If you're going to build a loop or you're going to buy one, don't buy one with small conductors. 3/4 inch diameter conductors on a 3 or 4 foot loop is too small. All right, number 4. To me, this is another biggie. This is my favorite. Construction material. As you well know, I'm a fan of metal foil tape, copper and aluminum foil tape. And the reason I am is because of its skin effect properties. Here's the skin depth. And you can see it's very thin. Copper, 1.4 mils, 1.4 thousandths of an inch at 80 meters, and 1/10 of a thousandth of an inch at 70 centimeters. And in aluminum, it's also thin too. But because of this, making a foil tape, making a loop does not have to be all metal. You don't have to go down to your hardware store, give up your 401k to buy enough copper pipe to build a magnetic loop out. Waste of money. Also a waste of weight, very heavy. You don't even have to make it out of solid aluminum. Just make it out of PVC pipe with some foil on the top of it, and it works just as good. This is a real optimization for mag loops. I show the comparison here. I priced this just a few days ago. 10-foot piece of 1.5 inch copper pipe, which is, by the way, nearly 2 inches on the outside, $116. And you need a couple of them to build a good mag loop. Piece of PVC pipe, same size, $14. Elbows to build these things, $12 for an 1.5 inch elbow, $2 for a plastic elbow. Oh yes, the plastic elbows work fine. And you may be thinking, oh, but copper's better than aluminum. No, it's not. It has twice as thick a skin. So it's an equally good material to build mag loops out of. Don't think you have to build mag loops out of copper. So there's the mag loop, Optimum mag loop, what I consider the middle of the road, epicenter for most hams. It's square. It's not round. It's not octagonal. Its size, well, it does not have to be less than 1/10 of a wavelength, but it needs to be around 4 foot. That's the optimum because it'll work all the bands. Conductor diameter, 2 inches minimum in a 4-foot loop. And it has to stay in proportion to size. So if you make it an 8-foot loop, it has to be 4 inches in diameter. Make it a 16-foot loop, it has to be 16 inches in diameter. Otherwise, efficiency will go in the dumper. And the material, don't make it out of copper or aluminum. Make it out of PVC and foil. That's the efficiency. That's the optimum loop. Now, tuning and matching. I'll show you an example here. Here's my optimized mag loop, an example of it. There it is. You've probably seen this picture already, although this is cut down so you can see the elements. Made out of 1.5 inch PVC, covered with aluminum foil, with PVC corners screwed together and lined inside with foil, held up by another piece of 1.5 inch pipe. And it has a coupling loop on it there on the right, made of 3 14-inch lengths of 1/2 inch aluminum tubing bolted to a piece of plastic in the middle, where the connector is. That's the basic design, held up by a cradle at the top. And the foil gap, you can see it at the top there for the loop where the capacitor goes. Notice you don't see the capacitor. It's there, though. You just can't see it. And here it is. Here's an actual picture of it. This is the one sitting in my backyard. I now know there are at least 2 more of these that have been built, and I'm going to show you the performance of them. Pretty spectacular. Here it is in my backyard. You can see the aluminum foil on the pipes. You can see the corner elbows where you can't see the foil because it's on the inside, but you can see the coupling loop on the right, which is 3 14-inch pieces of 1/2-inch tubing, and the feed point there at the bottom. I don't have the coax on in this particular picture, but it connects to that SO235 39 right there on that little square plastic piece at the bottom. All right, putting the tape on. This is a little difficult. I'll go through it quickly. You cut a strip that's 3 inches longer than the pipe, lay it down on a piece of carpet, fold the ends over, pull the little tab of the foil backing off the foil, and stick it to the carpet so it's nice and flat. Then pull the backing off so that the sticky surface is looking right up at you. And then push the pipe carefully, very carefully, right down in the middle of the tape. The tape, by the way, because you see here, is applied longitudinally. You don't wrap it around the pipe. You put it lengthwise on the pipe. 2 overlapping lengths of 4-inch aluminum foil tape. And a little tricky, but this way it's easy. You can cut the ends off after you're done, roll it back and forth, and it sticks on nice and smoothly. So you press it on the pipe, snip off the ends, roll the pipe over, smooth out the foil with the barrel of a plastic pen. And you apply 2 strips overlapped. The corners, and this comes from another one of our group here, W6OEK Jim, who's doesn't seem to be here today. You put the foil on the inside of the elbows. You cut this little shape, a little angle here, helps it go inside. This is a piece of the 4-inch aluminum tape, cut at this particular shape. And then you carefully apply it, take the backing off, and press it all inside of the corner elbows, which are cut in half longitudinally, as you can see. This is half the elbow. It's holes drilled in the side for sheet metal screws. And you trim it all down. This is all adhered in the inside. So when the tubing comes in from the sides, the aluminum foil on it sits right against those round areas on the left and the right and makes excellent contact so that the loop is conductive all the way around. Be careful, though, when you do this, not to split the tape. Okay, the tuning capacitor. This is probably the most novel part of this loop. Most hams like to use these expensive, costly, difficult methods to tune a loop. You don't need to go to that trouble. These are good ways to do it, but they're costly, and therefore they're not cost optimized. They are maybe performance optimized, but they're not cost optimized. The vacuum variable capacitor, ghastly expensive, and with the Russian thing not available at this time. And the big air variables, those are difficult, but that's what most home builders use. You don't have to. Here's a much simpler way. And here it is. There's the top of the mag loop. Inside the top pipe, piece of 1/2-inch, 1.5 PVC. Inside the top pipe goes a piece of 1-inch PVC, enlarged a little bit with some wrappings of cardboard. And it's also coated with aluminum foil, so that inside the outside foil of the loop is another piece of pipe, also with foil on it, making 2 plates of a capacitor, which can be moved back and forth inside the main loop with a couple of pull cords, which pull it back and forth for tuning. The couple of loops that have already been built have proven that this method works very slickly and very easily and tunes a very wide range. This tuning capacitor, as shown on that loop, tunes 31 megahertz to 12 megahertz without any external capacitor at all. So you can tune 20 meters all the way to 10 meters with just that piece of pipe inside, which costs a fraction of a big rotary capacitor or a vacuum variable at a 3/4 inch gap in the middle. Gap can be any size, frankly, but I use 3/4. Here's one of the corners showing the paracord coming out the end that pulls on the central movable piece. The advantage of this, this is beautifully protected from the weather, much better than any of the other forms. And it has a very high voltage rating. The maximum voltage in this capacitor is 2,000 volts on 40 meters, much less on 20, and almost of no concern at any lower frequency. Some guys suggested, well, why don't you just use those paracords and do it like they used to do back in shortwave radios and use it like dial cord? Well, one of my readers did that very thing. Here's his way of doing it. This is K5 DCC Denny, who lives near Chicago, and he used a sewing machine bobbin as a pulley in the end, and there his pull cord is coming out the inside of the pipe, going over the bobbin and then going down along the edge. He put it on the outside so it would make a good marker. I thought about putting it on the inside, but you can certainly use the old dial cord technique. And he used a few more sheet metal screws than I did, but you can see how the end of the loop looks. How about 40 meters? Can you get this loop down to 40 meters? Oh, yes, you can. You do this by using a mixture of the sliding capacitor and a shunt capacitor. And you can see the total amount of capacity needed here to tune up this 4-foot square loop, or it's actually a 45-inch square loop. It's not 48 because make it 48 and it won't quite tune the top at 10 meters. So I made it a little smaller. It's really a 45-inch square loop. And you can see it takes about 150 puff total to get it down to 40 meters, which is made up of an external shunt capacitor, a fixed capacitor, and the internal sliding capacitor, which you just saw, which will get you down to the arrow. What are the external tuning capacitors? I was surprised, but if you go on, you can buy these little 3,000 volt ceramic capacitors for nothing. I got these right off of eBay. I mean, not eBay, but Amazon. Just go on Amazon and search for high voltage ceramic capacitors, and you'll come up with them. And I bought this range of values. So by mixing them together, they're almost binary in sequence. Mixing them together, you get any amount of capacity. You need about 100 puff of them shunted across the sliding pipe capacitor to make the thing get down to 40 meters. I'm doing a little addition. I haven't finished it yet, but I'm going to use this little knife switch to actually switch in those capacitors on the outside. How about feed and match? Well, most hams use one of these three methods. The small loop, or the RF transformer there at the left, shown on that octagonal loop. Some hams use a toroid around the central loop, which in this case was a piece of RG8 coax, again too small, and some hams use gamma matches. I hate gamma matches. They're the hardest form of all matches, although they do work. The small inductive loop is flimsy, hard to mount. Selecting the toroid is difficult for the central method, and the gamma match, I never like gamma matches. They're very hard to build. Here again is my loop with the sliding capacitor inside. No external capacitor shown in this case, and the little matching network, which is in fact an auto transformer. It taps the loop just like as you see in this diagram, which you've probably seen in the past. You can tap a coil, a tuned coil, and it's resistive. So any place you tap it along the coil, it'll show you a purely resistive match impedance. All you got to do is slide the tap up and down until you find 50 ohms. That works so easily, but this is rugged and robust. And to close here, here's K5 DCC Denny contact. He made these FT8 contacts with his loop under a metal roof at ground level from his home there. You can see in the center of the United States. These are all verified FT8 contacts. You probably wouldn't have done quite as well on sideband, but I'm sure it would have worked just pretty well too. This is really verification of the loop. So if you build one, send me some pictures. Send me your ideas. This is still a thing in development, but at least it's now come to a reality. And there's my doggy and the QR code to get to me if you want to talk to me. And I'll cut it short there since I've taken quite a lot of time already.
John, that's fantastic. Thank you so much. When you're doing the joints for the foil between the elbows and the aluminum, is that just like a friction contact between those two, or did you put any, I don't know, kind of adhesive between the foils? Does that make any sense?
Yes. The foil inside the elbows is all stuck inside of the elbow with its own self-adhesive. But where it makes contact on the round, smooth ends of the elbow is where the pipes come in, and they also have foil on them, and they sit right. It's just a pressure fit caused by the sheet metal screws that hold them. They hold the two halves of the elbows cut longitudinally down the middle, and makes great contact.
Okay, and the tape, you said no real difference between copper and aluminum?
No real difference. Copper is not necessary. 4-inch aluminum tape, easy to get on the internet. So is 2-inch, 1-inch, half-inch, quarter-inch, but copper is too. If you want to build it out of copper, go ahead, but you won't buy yourself anything except more money.
Okay. Any other questions from the team? Dan, go ahead.
So John, is there any effect of the adhesive, like where you've got tape overlapping tape, right? You're wrapping 2 strips to go around that pipe.
No.
Right? And you've got adhesive in between, of course, the two.
No. What happens if you put 2 metal plates close together with a dielectric between them? What do you got?
Well, it's a capacitor.
A capacitor. What does a capacitor look like to an RF current? A low impedance. Capacity through the adhesive makes the overlap of tape completely ignore the adhesive, as long as you give it about 1 inch or so. And that's why I put it on longitudinally. You've got about two 1-inch overlaps when you wrap 2 4-inch pieces around a piece of 1.5 PVC, which, by the way, is 1.9 inches outside, or nearly 2 inches.
Great, thank you.
So I just wanted to comment on the mythology of the 10% rule or the 10% guideline. I agree with everything John said, but one thing about the diameter of the loop, keeping it small, is you're trying to get a constant current effect through the loop, because your broadside null from in your radiation pattern comes from the constant current.
That is correct.
Right. And so if you want to have a good broadside null off your loop, keep it under 10%.
Yeah, that's correct.
Right.
That's correct. If that's one of your objectives.
Yeah, if that's one of your objectives. And if not, as you get up towards 50%, your loop begins to transition into a full wave loop.
An ordinary loop.
Yeah. And that has completely different, in fact, completely orthogonal radiation patterns, right?
That is correct.
Yeah.
The radiation pattern of a small loop at under 10% is this way. Radiation pattern of a larger loop or a smaller loop made bigger is more this way.
Right.
So it depends on what kind of a radiation pattern you have to optimize for what you consider the optimum point. Maximum frequency, low efficiency, conductor, cheap, cost, neighbor appeal, all of those factors. You got this whole group of factors you need to optimize. My little 4-foot loop to me is a kind of what I call the epicenter of most hams.
Very good. Any other questions?
Anyway, thanks for letting me do it. I wanted to put it out because I think this design is going to do me probably more good than anything else I've done. I think it'll become a flagship design.
Very good. Thank you so much, John. I really appreciate it. Oh, one
John,
more question, Randy?
Yeah, John, how do you attach the extra capacitors to the loop there?
Okay. I haven't finished it yet, and this is one part, but it's on my workbench to be finished. But it's basically a couple of aluminum strips with a couple of gaps and a piece of plastic plexiglass strip on top.